Hi, I'm Christoph and I will present our work Beyond SOT, Tracking Multiple Generic Objects at Once. This work was done during an internship at Google Research. Let's assume we are given multiple user-defined bounding boxes in the initial frame of the video. But how can we now use these initial annotations to track these objects in the remaining frames of the video? The natural way would be to use multi-object trackers, but a multi-object tracker can only detect and track objects that correspond to predefined class categories. In this example, the MOT method is, for example, unable to track the Rubik's Cube because it was not part of the training data. Since a multi-object tracker is not able to track multiple generic objects, we could instead employ multiple single-object trackers. In this scenario, each tracker would track one object. This works, but the runtime grows linearly with the number of targets. In addition, we missed the opportunity to reason jointly and increase the tracking robustness. Thus, we propose in this work the task of generic object tracking that no longer focuses on tracking a single, but instead multiple generic objects at the same time. To advance research that focuses on tracking multiple generic objects, we propose a new benchmark LaGOT, and the first multi-object GOT tracker, Thomas. SOT contains diverse and relatively long videos with challenging tracking scenarios, but SOT provides only annotations for a single object in each video, but typically multiple objects are present throughout the full sequences and are fairly difficult to track. Thus, instead of collecting the new videos, we use the SOT evaluation set and add annotations for up to 9 generic objects in each sequence. The resulting evaluation length of LaGOT is almost 3 times longer than SOT. It contains 10 times more class categories than Gmod 40, and the average track length of LaGOT is 3 times longer than in Tau, and almost 10 times longer than in Gmod 40. So now let's focus on our tracking method. To track multiple generic objects at once, our method needs to meet several requirements. It must be able to track a variable amount of objects in different videos. It might need to track objects of very similar or completely different classes in a video. Lastly, it is crucial that such a method uses shared representations for multiple targets to reduce the computational cost. For all these reasons, we designed Thomas as follows. Thomas operates on the full frame and uses a backbone to extract features from the training and test frames. Then we feed the bounding boxes of the training frame together with the training features to the multi-object encoder that then generates multiple feature maps that encode the location of one target object each. In order to combine these feature maps into a single feature map, we randomly sample an object encoding from a pool for each target. Then we multiply each embedding with its feature map and sum them. Afterwards, we combine these encoded training frame features with the test frame features and feed them into the transformer encoder that propagates the target information from the training frame to the test frame. Now we feed the refined features to the transformer decoder that we query with the very same object embeddings that we used for encoding each target. The decoder then produces the target model for each target object. Finally, we apply these target models on the refined test frame features in order to localize the targets in the test frame and regress their bounding boxes. Running Thomas on different LaGOT sequences produces the following outputs. Note that Thomas can track multiple objects corresponding to very similar or completely different class categories at the same time. To measure the performance of a tracker on LaGOT, we use popular SOT tracking metrics that we compute for each target object separately, and average. Since the targets are often occluded or out of view, we focus on the long-term tracking metric, WhatLT. Since Thomas is the first generic tracker that tracks multiple objects at once, we compare it with recent SOT trackers that we run for each target individually. Thomas achieves the best results in terms of success or F1 score. Furthermore, we observe that Thomas achieves a faster runtime than its related SOT method, Tom, when tracking more than 2 objects at the same time in a video sequence. Note that Thomas achieves almost a linear runtime. Lastly, we also evaluate Thomas on popular SOT benchmarks, where it achieves competitive results and even sets a new state-of-the-art on TrackingNet. Thank you for watching. Code and data are available online.